Hello everyone, this video is going over the Unit 3 practice exam for Physics 251. Number 1. A 50-gram ball is dropped from 2.00 meters and bounces up to 1.50 meters. The ball remains in contact with the floor for 7.00 milliseconds. Calculate the ball's momentum right before hitting the floor, right after leaving the floor, the impulse on the ball from the floor, and the average force exerted on the ball by the floor. Okay, so the first part of this problem is just an ordinary kinematics problem. We have an initial vertical position. We've got a final vertical position. We have an initial vertical velocity, so that at t is equal to 0, the ball has no momentum. And we know that we have enough information to figure out how quickly it's going to be moving right before it hits the floor. So I've called that V1. So at T2, that's going to represent the point in time where the ball separates away from the floor, and then it's going to go up to this position that it has at time T3. So first, let's just start with kinematics. I have enough information to use the time-independent kinematic equations in order to figure out the values of V1 and V2. So I know that the ball is just experiencing free fall between t is equal to 0 and I guess T0 and T1. So I can determine the velocity right before it hits the floor. That's 6.261 meters per second in the negative direction. Remember, the time-independent kinematic equations always give you a speed. And then finally, I do the same thing for V2, and I get a different velocity, so 5.422 meters per second up. Now, part of the reason why those velocities are different has to do with the fact that the ball bounces, so it's got some distortion that it experiences, but knowing V1 and V2 means that we can figure out what the momenta P1 and P2 are. I'm just taking the mass of the ball times the velocity in each case, where I do need to pay attention to the sign, and I end up with negative 0.313 kilogram meters per second for the momentum at time 1, and positive 2.71 kilogram meters per second for the momentum at time 2. The impulse is going to be the change in momentum. And we're concerned with the impulse that the floor delivers to the ball. So I can take the difference between P2 and P1, that's going to be capital J, which is the impulse, and I get positive 0.584 either kilogram meters per second or 0.584 Newton seconds. Now, Newton seconds and kilogram meter seconds are identical to one another, but when we're talking about impulse, you'll just see Newton seconds more frequently. When you're talking about momentum, you'll see kilogram meters per second. So this is a positive impulse, which makes sense with the decision that we made further up here concerning our coordinate system. I have the initial position as a positive. The final position is going to be ground level, so y1 is going to be equal to 0. y2 is also equal to 0. So the force that the floor exerts on the ball is one that's going to be directed in the positive direction. Now for the average force, I can take the impulse and divide that by the delta t. So this is the first time that we've needed to worry about the amount of time that the ball spent in contact with the floor. Once again, we get a positive force, which makes sense with our positive impulse, and that average force is approximately 83.5 newtons when sig figs are applied. Number 2, an object at rest explodes into 3 pieces with equal mass. After the explosion, the first piece moves at 20.0 meters per second due east, and the second moves at 30.0 meters per second southeast. What's the object's initial momentum? What's the velocity of the third piece? So you can think of an explosion as a collision in reverse. So if all of the pieces start off with 0 velocity before the explosion takes place, I know that the total momentum of the system is going to be 0 as well, even though each of the pieces is going to be moving at some non-zero velocity. All I know about the object that explodes is that it splits into 3 pieces with equal mass. So I'm just going to call each of those individual masses m, such that the original mass was 3m. So I can take the momentum equation, where I know that P initial for piece 1 is going to be the mass of piece 1 times the initial velocity of piece 1, which is 0. So I'm going to get 0 for the initial momentum of both piece 1, or all pieces, 1, 2, and 3. I know about 2 out of the 3 pieces and how they behave after the explosion has taken place. So piece 1 is moving due east, so that's in the positive x direction. Piece 2 is moving southeast, and because I'm not given any angles or anything like that, you can interpret southeast to imply that it is 45 degrees between south and east. So this angle theta is 45 degrees. So V2 has a horizontal component and a vertical component, and then V3 is the one that we don't know anything about. We can use the law of conservation of momentum here, such that the final momentum of piece 1 is going to be that mass m times the velocity of piece 1. And in the x direction, that velocity has a magnitude of 20.0 meters per second. But in the y direction, there is no y component. So I can say p final y for piece 2, or that should be piece 1 actually, is going to be m is equal to, or m times 0 meters per second. Now for piece 2, I know that the mass is just m. I know that V2's velocity, the magnitude is 30 meters per second, but I can break this down into a V2x and a V2y, where for the y component, I'm going to abide by the rules of this coordinate system and say that this downward velocity is something I can treat as a negative. So I don't get a numerical value for the for the momentum of piece 2 after the explosion, but I know that the momenta are going to break into equal parts, one in the x direction, one in the y direction, where the one in the y direction is also in the negative direction. Now, this next statement right here is my my momentum conservation statement. So this is a capital P initial x. So the total momentum in the x direction before the collision has to be equal to the total momentum in the x direction after the collision. And I know that that's going to be the sum of the final momenta, all in the x direction. So P final x1 plus P final x2 plus P final x3. I know that they add to 0. So I can write an expression that just gives me a way to relate the mass of the pieces to the 2 velocity components that I know, and then, of course, P final x3, which I don't yet know. So P final x3 is going to be equal to negative m times 41.213 meters per second. That's just the combination of 20 meters per second and 21.213 meters per second multiplied by negative 1. I can do the same thing for the y direction, such that the total initial momentum in the y direction is equal to the total final momentum in the y direction, which is going to be the sum of the final momenta in the y direction for piece 1, piece 2, and piece 3. If I plug that into this expression, retaining the negative that I have to keep there for P final y2, because that piece points down, I end up with the expression PFY3, so the final momentum in the y direction for piece 3, is equal to the mass times 21.213 meters per second. I can determine what the final velocity is for piece 3 by figuring out the magnitude of the momentum vector, P final 3. So that's just the square of the horizontal component added to the square of the vertical component under a square root. And I end up with m times the square root of 2,148.528, and this is meters squared over seconds squared. That means that I can take v final 3 as just the momentum, p final 3, with the mass divided out. So all I'm doing is dividing out this m and then carrying through this square root, and I get 46.3522 meters per second. So that's 46.4 meters per second if I apply sig figs. Knowing the magnitude of the final velocity in the x direction and the final velocity in the y direction, which I can find just by taking pfx3 and dividing the mass out. That just leaves me with the velocity. I have a negative velocity component for the horizontal direction. I have a positive velocity component for the y direction. And this is something that you might have been able to guess just by looking at the before and the after. I've got 3 pieces. I know one piece ends up with a final velocity that's oriented toward the right, another piece that is oriented down and toward the right. So the third one should have an orientation that's just roughly up and to the left. And I can see that that is indeed the case for this final velocity vector. So I am first setting up a right triangle so that I can find this angle alpha. That's just going to be the inverse tangent of the y component's magnitude over the x component's magnitude. So that's 27.2 degrees. But expressing that angle with respect to positive x just involves taking 180 degrees and subtracting that alpha off. That's where we get 153 degrees. Number 3, a squirrel darts into the road ahead of a 2,000 kilogram car moving at 12.0 meters per second. The driver slams on the brakes when the squirrel is 20.0 meters in front of the car. The car's brake pads can provide 8,000 newtons of friction. Will the driver hit the squirrel? So this is phrased as a yes-no question. However, there are 3 ways that we can solve for this to confirm that the driver does not hit the squirrel. And the first one just involves making a simple diagram that represents the car while it's slowing down. So at t is equal to 0, I have my car of mass m that is moving at 12.0 meters per second, and it hasn't yet started to decelerate, so let's call that position x is equal to 0. I know at some later time the car is going to come to rest, so t final is unknown, but I know v final is 0 meters per second, and I don't yet know what x final is, but I can figure it out. And the key is to recognize that the acceleration that the car experiences has to be oriented toward the negative x direction, and in that interval, this is what the free body diagram would look like. There's a gravitational force pointing down, a normal force that's exactly as big, but just in the opposite direction, oriented up. And then the force of the brakes is what ultimately will cause the car to come to rest. So F net is going to be oriented in the negative x direction. All of the methods that we can use to solve this problem involve energy conservation in some sense. We can start with the work kinetic energy theorem for method 1 to figure out what the stopping distance would be if the brakes were being used at full strength. I know exactly how much kinetic energy the car has to lose in order to come to rest, because I know v final x is going to be 0. I've got the mass of the car and the initial velocity. And I know that that can be balanced against the work done by friction, where there's a negative sign here because the brakes are going to result in a force that's going to produce a negative acceleration. That just means an acceleration oriented toward the negative side of our coordinate system. So I have a negative that comes from the initial kinetic energy being subtracted by 0, or from 0. I have a negative that cancels out here, and I get a delta x that's a positive, and it's 18.0 meters. So if the squirrel was 20 meters ahead of the car, and the car only needed 18 meters to stop, that means that there's a 2-meter buffer between the car and the squirrel. So method 2 If I calculate the amount of work that the brakes can do at full strength over 20 meters, if that amount of work is larger in magnitude than the change in kinetic energy, I know that the car stops in time. If it's equal, I would know that the car stops at exactly 20 meters. And if it's more, that would mean that the car needs a distance greater than 20 meters to come to rest. So the work done by the brakes is just the magnitude and direction of the force that the brakes provide, so negative 8,000 newtons, times delta x, which is the distance between the car and the squirrel. I end up with negative 160,000 joules. And I know from the previous calculation that the loss of kinetic energy is going to be negative 144,000 joules. So since that magnitude is less than what the brakes can do, that means that the car can stop before hitting the squirrel. And method number 3, I can figure out how much friction is required in order to bring the car to rest in 20 meters. This actual braking force is different than the 8,000 Newton braking force that we were quoted above. It takes, again, the amount of kinetic energy that the car has to lose in order to come to rest, and it divides it by 20 meters. So I have a negative force, which makes sense, but the magnitude is below what the maximum that the brakes can provide is. So if you apply the brakes at full strength, that means that the car is going to stop in fewer than 20 meters. So the squirrel doesn't get hit. Number 4, the driver from the previous question accelerates back to 12 meters per second and then rear ends a 2,500 kilogram truck moving at 8 meters per second. What's the total momentum of the system before the collision? And if the vehicles collide inelastically, what's their shared velocity right after the collision? So I have the same car from the previous problem, so that's a mass of 2,000 kilograms, and the initial velocity for this collision is back up to 12 meters per second. The initial momentum of our system before the crash is going to be the sum of the momentum of the car and the momentum of the truck. So momentum is just mass times velocity. So the total initial momentum is the mass of the car times the car's initial velocity, plus the mass of the truck times the truck's initial velocity. This gives 44,000 kilogram meters per second because momentum units are just mass units times velocity units. Now, afterward, I know that the total momentum of the system has to be the same value, so 44,000 kilogram meters per second. The combined mass for this inelastic collision is going to be 4,500 kilograms, so I can divide to figure out what the final velocity is. And I get 9.7 repeating meters per second, which to 2 sig figs is 9.78 meters per second. Number 5. A 15-gram rubber bullet moving at 500 meters per second undergoes an elastic collision with a stationary 40-gram wood block. What are the velocities of the bullet and block after the collision? So compared to that previous problem where we had 2 cars that collided and then stuck together, since this is an elastic collision, both the bullet and the block are going to move separately after the collision's taken place. So that means that I can use this pair of final velocity equations. And I kind of put a little bit of emphasis on this because this expression is not a one-size-fits-all. It is specific to this case here, where you have 2 items, M1 and M2, where M2 is at rest, M1 crashes into it, and then they both have non-zero velocities after the fact. This final velocity expression only works for this scenario. So I have the expression for the final velocity of item 1 in the x direction. That's going to be the difference between the masses divided by the sum, multiplied by the one non-zero initial velocity I have, which is the one that I can attribute to the bullet. Now, because I'm using these masses to produce a ratio, I just need to make sure that the masses have the same units. They don't necessarily need to be kilograms before I proceed with this. So I'm going to stay with grams. I've got 15 minus 40 divided by 15 plus 40. That's going to yield the ratio negative 25 over 55. And I have grams on the top and grams on the bottom. So ultimately that mass unit cancels out as long as the top and bottom match. I end up with a negative velocity, which makes sense when you think about how that bullet's velocity has to change. It starts with a positive velocity, and after interacting with the block, it's got a negative velocity. So it makes sense that I have negative 227 meters per second when sig figs are applied. Now for item 2, the final velocity expression is different. It's 2 times m1 divided by the sum of the masses. That is going to be multiplied by v initial x1. So that yields the ratio 30 grams over 55 grams. And I can multiply that by 500 meters per second, and I get a positive velocity, which makes sense because that block has to go from not moving at all to moving in the positive x direction. And when I apply sig figs, I have 273 meters per second. So the velocity of the bullet is not conserved itself, but there is a way that you can perform a check just to make sure that you've evaluated the problem correctly. And that is to look at the magnitude of the final speeds that you have, so 227 and 273 meters per second. That should add up to the magnitude of the initial velocity of the moving object. And you'll see when I take these two and add them together, I do get back to 500 meters per second. Number 6, a spring of length L stretches 10 centimeters when attached to a 200-gram block. What is the spring constant? How much work is required to stretch it the first 5 centimeters from its equilibrium position, and how much more work is required to stretch it the next 5 centimeters. Okay, so first off, we've got a spring and a block that begin at equilibrium. So the spring is stretched out, but I know that the forces acting on the block cancel. So F spring is exactly as big as it needs to be to counteract the gravitational force. And F net in the y direction is going to be 0. I don't know the initial length of the spring, but I know I can call that L0, and I know that the stretched length is L0 plus 10 additional centimeters. I know enough to figure out what the spring constant is because I know the mass of the block and I know the displacement that the spring experienced when the block was connected to it. Here I'm just calculating the absolute value of this ratio, the spring force over delta y. So the spring constant is 19.6 newtons per meter. Now the work that needs to be done in order to stretch it the first 5 centimeters is not just what you would get if you used Hooke's law, which is this expression right here. If you plugged in a 5 centimeter and then multiplied by the spring constant that we just got, the spring force would tell you the force that you have to exert in order to get the spring to stretch from a displacement of 0 to a displacement of 5 centimeters. But that is not the average force that you would have to overcome in order to stretch the spring. Instead, it's the maximum. So in order to figure out how much energy you have to put into the system when you're stretching the spring, use the potential energy expression. I know the elastic potential energy for this spring is going to depend on 1/2 the spring constant we just calculated, and then delta y quantity squared, where for us delta y is 5 centimeters, so that's 0.050 meters. And that translates to 0.0245 joules of energy. Because the block is not oscillating, that potential energy is going to be equal to the work done by really the gravitational force in causing the spring to stretch out by 5 centimeters, just to start with. So in other words, the mechanical energy of this system is all potential. There's no kinetic because the block's not moving. So that work also would have to be equal to 2.45 times 10 to the negative 2 joules. Now, what can be a little tricky here, or maybe initially counterintuitive, is the fact that it's going to take more work for you to stretch from 5 centimeters to 10 centimeters than what it costs you to go from 0 to 5. That's because every time you cause the spring to undergo some displacement of, let's say, 1 centimeter, you have to work a little bit harder in order to stretch the next centimeter and a little bit harder to stretch the next centimeter and so on. So we can figure out what the total elastic potential energy in the spring is after you've stretched it the entire 10 centimeters. That's 0.0980 joules. And then just subtract off the work that we already calculated in the first part of this problem. So 0.0980 joules minus 0.0245 joules leaves you with 0.0735 joules. It's not just a 50-50 split. So it requires more effort for you to stretch the last 5 centimeters than it did for you to stretch the first 5 centimeters. Seven, the spring from the previous question is pulled 0.100 meters to the right and then released at t is equal to 0 seconds. The block's position can be described by the function x as a function of t is equal to the amplitude times the cosine of the angular frequency times time plus the phase constant. We can assume that damping and frictional forces are negligible. Calculate the system's total mechanical energy, the block's maximum speed, the oscillation period, the oscillating block's angular frequency, the block's speed when the system's mechanical energy is evenly split, and the spring's extension when the system's mechanical energy is evenly split. Starting with part A, I have enough information to figure out what the maximum elastic potential energy in this system is. I know that's going to correspond with the times when the block is at a position of either plus 10 centimeters or minus 10 centimeters, because compression and expansion both add potential energy, or they both create potential energy. So I can take the spring constant we calculated in the previous question, 19.6 Newton meters. If I plug that into our elastic potential energy expression, I find the maximum elastic potential energy is identical to the value we calculated at the end of question 6. It's 0.0980 joules. Now, I know that the maximum speed and the maximum elastic potential energy can't happen at the same time. The maximum speed happens when the spring is instantaneously neither stretched nor compressed. So in other words, all of that potential energy will have transformed into kinetic energy. So K maximum is going to be the same value, 0.0980 joules. I can use the kinetic energy expression and solve it for the maximum speed to figure out what that maximum speed is. And we get 0.990 meters per second. From here, now the oscillation period. There are a couple of equations that I could use to figure out what the oscillation period is. The most straightforward one, the one that gets us there in one step, is this one. So if I take 2 pi times the square root of the ratio m over k, I'll end up with 0.635 seconds when sig figs are applied. And just to go through what's happening with the units here, newtons per meter is the equivalent of kilograms per square second, even though that's a really strange way to think about a spring constant. Nonetheless, when you take kilograms and then divide it by kilograms per second squared, you just end up with seconds squared underneath the radical. So taking a square root is going to leave you with a time that's in seconds squared. Just in seconds. The angular frequency omega is also something that I could calculate a couple of different ways. One would be to take the square root of the ratio k over m. That's exactly the same as taking the period from our previous part of the problem and then just plugging it into this expression, because omega is going to be equal to 2 pi over the period no matter what. So we end up with 9.90 radian per second, because now I've got 2 pi radian in the numerator and then seconds in the denominator. Next, I want to figure out what the speed of the block is when the kinetic energy and the elastic potential energy are evenly split. So this is not a brand new oscillation. I'm still going to use the same total energy that I had before, which was 0.0980 joules, and split it into halves, so that when the kinetic energy is exactly half that value, I can set it equal to 1/2 mv squared, where this v is no longer representative of v max. It's just the v that corresponds with this specific kinetic energy value. If v is going to be the square root of 2 times the kinetic energy divided by the mass, the value I end up with is 0.700 meters per second. So not simply 1/2 of the maximum speed that we calculated a bit earlier. That maximum speed is 0.990 meters per second. When the elastic potential energy is equal to exactly 1/2 of the total system energy, I can set that value equal to 1/2 k times delta x, where again, this delta x is not the entire amplitude this time. It's just the spring distortion or the spring displacement that I can correlate to half of the elastic potential energy of the system. So delta x here is going to be the square root of 2 times the elastic potential energy divided by the spring constant, and I get 7.07 centimeters. It's not simply 1/2 of the amplitude that we started off with, because the amplitude was 10 centimeters. Number 8, an 8 kilogram block is released from the top of a ramp made from a 1.20 meter board that's angled 30 degrees above horizontal. It reaches the bottom of the incline 2.75 seconds after it's released. A frictional force impedes the motion of the block. What's the initial mechanical energy of the block? What's the block's speed at the bottom of the ramp? What's the final mechanical energy of the block? How much work was done by the frictional force? What is the coefficient of friction between the block and the board? So we've seen versions of this problem in Unit 2 that we could approach just using what we knew about kinematics and dynamics. This problem is going to involve a combination of kinematics, dynamics, and also energy conservation. So here's our scenario. I've got my ramp that's inclined some angle theta above horizontal. This is what my free body diagram would look like for that ramp, where there's a normal force that's perpendicular to the surface, and it's going to be canceled out by the cosine component of the gravitational force. And then I have this kinetic friction force that's pointing uphill, and then Fg sine theta, where I have a net force relative to the surface of the ramp that's non-zero. If that were not the case, then the nature of the friction that would be acting on that block would be static, because it would be preventing the block from sliding downhill. In other words, it would allow the block to stay at static equilibrium. But here, I know that the block starts off with zero velocity and it ends up with a non-zero one by the bottom of the ramp. So the block is speeding up as it gets closer to the bottom of the ramp. That by itself is enough for us to know that the acceleration along the surface of the ramp is not just going to be free fall acceleration times sine theta. That would be sensible if this were a smooth ramp. But since it isn't, we need to do more. We can use what we know about this situation to figure out what it must be. Now, part A is asking for the initial mechanical energy of the block. And because there are no springs involved here, the mechanical energy is just going to depend on the gravitational potential energy and the kinetic energy. So the total energy at t is equal to 0 seconds, I'm going to call that E initial. It's going to be just the gravitational potential energy plus 0 because the block isn't pushed down the hill, it's just set at the top of the ramp. That means that the gravitational potential energy is all that's there to work with. So I can figure that out because I know that the ramp has a length, like the hypotenuse has a length of 1.20 meters. So I can take that hypotenuse times the sine of 30. That's got to tell me what this y component here is. And that works out to 47 joules of mechanical energy. To figure out V final without already knowing something about like the coefficient of kinetic friction between the block and the surface, that's going to require us to use that time that we were given in the beginning of the problem. I know that there's an acceleration relative to the surface of the ramp, so I'm going to call that AS for the s-axis. I'm setting my coordinate system up such that the values get more positive along the s-axis as you get closer to the bottom of the ramp. So in other words, forward is positive s. That means that the acceleration AS I'm going to get is going to be something that's positive value. And all I have to do is rearrange this first kinematic equation for position so that I can solve for AS. And I get 0.317355 meters per second squared. So quite a bit less than what you would get if you just took free fall acceleration and multiplied it by sine 30. Now that I know that acceleration, I can take the time that we were given and use it to figure out the velocity at the bottom of the ramp. So VF in the S direction is just going to be 0.873 meters per second when sig figs are applied. So now that I know that, I know exactly how to figure out how much kinetic energy the block has at the bottom of the ramp. I know the block's mass is 8 kilograms. I just figured out what the block's speed is at the bottom of the ramp. So 1/2 mass times speed squared is going to give us approximately 3.05 joules of kinetic energy. This tells me where the remaining 44 joules of energy had to go, because I had 47.04 joules of energy at the top of the ramp, and now I can only account for 3.05 joules. That remaining 44.0 joules had to go into negative work. So think about the orientation of the kinetic friction force vector relative to the displacement vector. They'd be anti-parallel. Our displacement vector would point downhill. Fk, the kinetic friction vector, would point uphill. So if I take the ratio of that work and then the length of the ramp, I get the force of friction, kinetic friction in particular. So that's negative 36.6612 newtons, negative because that's pointing in the direction that I've called negative for the surface of that ramp. And at this point, I can come back to some dynamics stuff. So my free body diagram that's further up here. Fk is going to depend on the normal force and then the coefficient of kinetic friction. That's what I don't know. But I know that the normal force has a magnitude that is the gravitational force's cosine component. So that means Fk is going to be mu k times the normal force, where this is just written out for absolute value. That means that mu k is going to be the magnitude of the frictional force I just calculated divided by mg cosine theta, where 30 degrees is our angle theta. And when you apply sig figs, you get 0.540 for the coefficient of kinetic friction. That has no units because these are newtons on the top, newtons on the bottom. Number 9, two blocks are placed on opposite ends of a 2.00 meter long, 5.00 kilogram beam that rests on a support 0.25 meters from its right end. Block 1 has a mass of 8 kilograms and the system is in static equilibrium. So this is a net torque problem, and the fact that our system is in static equilibrium tells us that the net torque is going to be equal to 0. Now, I know the mass of one block. I don't know the mass of the other, but I know the mass of the beam, and I know where the fulcrum or the support is placed. It's 25 centimeters away from the right edge. So what I can do here is to write an expression for the torque produced by each of these blocks individually, and then I can figure out what has to be left over in order for the net torque to be equal to 0. Because I don't know anything about M2, I can't figure out what the normal force provided by this fulcrum is. But I can get around that by choosing a rotation axis that is right above the fulcrum, such that the torque produced by that normal force has to be 0, even though I don't know how big the normal force is yet. That means that if 0 is here, all values to the right-hand side of that fulcrum are going to be positives. So this end of the beam where block M2 sits is going to be positive 0.250 meters. The center of mass for the beam, which is just at the midpoint, is going to be 75 centimeters to the left of the fulcrum. So that is going to be negative 0.750 meters. And then block 1 is 1 meter away from the center of mass, so negative 1.75 meters. The torque produced by block 1 is going to be a gravitational one. So I can take R1, which is going to be the moment arm, times Fg1, where Fg1 is just the gravitational force acting on the beam. And if I think about the gravitational force that block M1 is exerting on the beam, that force is going to be directed toward the floor, so downward, in other words. And that would be enough to cause the system to experience a counterclockwise rotation, if this gravitational force were the only one that I were dealing with. So that means I should have a positive torque. And I do have one because I have a downward force, so that means that I'm using negative 9.80 meters per second squared, and the moment arm's a negative. So this yields 137 Newton meters, because we don't combine the Newton and the meter to a joule when we're talking about rotation, as opposed to energy. Next, the torque produced by the beam can be determined by pretending that all of the beam's mass was located at its center of mass, which I know is negative 0.75 meters to the left of my fulcrum. So our beam is negative 0.50 meters. The beam's mass is 5 kilograms. I'm using free fall acceleration in its negative form because I know the gravitational force is going to be oriented downward. That gives me another positive torque, just one that's not as large as what I had before. And my only unknown non-zero torque is the one that I can attribute to box M2. So if tau net's going to be equal to 0, I know that all of these torques have to sum to 0. That tells me that the torque for produced by box 2 will have to be a negative to cancel out the two positives that we've already determined. And that negative magnitude, or that negative value, is about negative 1.74 Newton meters. I don't know anything about the mass of block 2, but I know where it is. And I know that this is a problem that's taking place on or near Earth's surface. So that means I have enough to solve for M2 once I know tau 2. I get a negative torque divided by 0.250 meters, which is a positive, but I'm dividing by negative 9.80 meters per second squared. So I get a positive mass. That would be 71.0 kilograms when sig figs are applied. Last but not least, because I now know the mass of M2, I can figure out what the normal force has to be. It's got to be the lone upward force that is opposing the gravitational force from block 1, the gravitational force from block 2, and the gravitational force of the beam itself, or Earth acting on the beam itself. So that's just going to be the sum of all the other gravitational forces that are known. I can just add those masses together, multiply by free fall acceleration, and I get a normal force of 823 newtons. Then last, number 10, a cable is used to secure a 3.0 meter beam to a wall, as shown below. A block of mass M is suspended 2.10 meters from the pivot. The beam itself has a mass of 40 kilograms. The cable is rated to provide a maximum force of 2,000 newtons. What is the largest mass that the cable can support? And if the block is removed and the cable is quickly severed, how much angular momentum would the beam have right before it hits the wall? So for part A, this is just another net torque problem where I know that tau net is going to be equal to 0 initially. So the torque of the block added to the gravitational torque on the beam added to the torque produced by the cable will give a 0. And it makes sense for us to put the 0 on our coordinate system right here where the rotation axis is so that all of our moment arms are positive. And I can look at the forces that are directed downward. So the gravitational force on the block, that's going to be a negative force. The gravitational force acting on the beam is also going to be directed in the negative direction. And I've got the cable. That tension is the only one that's got a component along the positive y-axis. The x component of the tension is going to be the same magnitude as the normal force, but it's simply lined up incorrectly to actually provide a torque about this pivot point right here. So I don't need to consider the cosine component of this tension. I don't know the mass or the value of M, the mass that is located at 2.10 meters, but I know everything else, and I know that these torques add to 0. I can solve for that mass, and I end up with 117 kilograms. So that means that 118 kilograms would cause the cable to need to provide more than 2,000 newtons. And that means that, for example, 116 kilograms would require that the cable provide a force that is smaller still than 2,000 newtons. Now for part B, there's a little bit of an oversimplification happening here. We're imagining that the block is gone and that we're just considering the gravitational torque about this pivot point if the cable were snipped. In order to figure out how much angular momentum the beam has right before it hits the wall, I would need to know two things. First, the moment of inertia for this beam about one end. I could model it like a thin rod, just as we modeled the meter stick in lecture. So this is 1/3 ml squared, where I know the mass of the beam, I know the length of the beam. That moment of inertia is 120 kilogram meters squared. If the cable is gone and the dangling mass is removed, that means it is only the gravitational force acting on the beam that provides the net torque. So tau net is the torque the gravitational torque about the beam, where that beam's gravitational force is something that I can determine. That is just 40 kilograms. Not the gravitational force, it's the gravitational torque further up here. So negative 5.88 Newton meters, which was one of the interstitial calculations from the previous problem. I could divide that by the moment of inertia that we just calculated, and I get negative 4.90 radian per second squared. Negative because severing the cable would cause this entire beam to experience a clockwise rotation, and clockwise torques are going to be negatives. Now, if I know what the angular acceleration is, which is what I get from taking a torque and dividing it by a moment of inertia, I can use that with a rotational kinematic equation. Omega final is unknown, but I know that omega initial is 0. I know that alpha has a value of negative 4.90 radian per second squared, and the delta theta that this would swing through would just be negative 90 degrees. Visualize where this beam would land after you snipped the cable and you let it come to rest. It would just be hanging straight down, so that would be an angle of negative pi over 2 radian. So I end up with a final angular velocity that's approximately 3.92 radian per second clockwise. So I need to treat that as a negative. This is the time-independent kinematic equation, once again giving me a speed that it's up to me to determine whether that is clockwise or counterclockwise. So that's a negative. Now that I know what that omega final is, I can calculate the maximum angular momentum at the end of that process. It's just the moment of inertia times omega final, where this is where we get negative 471 kilogram times meter squared over second, because these are just moment of inertia units times angular velocity units. So kilograms times meter squared, all multiplied by radian per second. So I noted that there is a bit of an oversimplification at work here, and it's due to the fact that the angle between the gravitational force vector that I can imagine is acting at the center of mass of this beam and the rotation, the radial line, the line that would cut from the rotation axis right down the body of this, that angle is going to change over time. So what I've found here is really the maximum angular momentum. And I apologize that the scan chops it off a little bit, but let's say this L final represents a maximum. So this is a negative because it's clockwise. However, every time the beam changes its angular position, it's going to change the component of the gravitational force that's capable of exerting a torque. So this is like an idealized maximum value.